KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss first one example problem, that is example 10.7. அதுக்கப்புறம் next continuation theoretical topic, that is what applications, right? Blood flow and heart attack. After completion of that, one more important application, that is what dynamic lift. So this dynamic lift helps us to understand, that is the movement of aeroplane, that is what aircraft wing. So what is the shape of the aeroplane wing or aircraft wing and how it is going to move. That and all you can see with this application, that is what dynamic lift. Okay, right. See here, ma. So in this class, initially that is what first example problem, that is example 10.7, based on blood velocity. Based on blood velocity. Okay, ma? Right. Say this. The flow of blood in a large artery of an anesthetized, right, anesthetized dog is diverted through a venturi meter, right? Okay. Ipo the wider part of the meter has a cross sectional area equal to that of the artery. A is equal to 8 millimeter square. The narrower part has an area A is equal to 4 millimeter square. Full stop. The pressure drop in the artery is 24 pascals. Full stop. Finally, what is the speed of the blood? What is the speed of the blood in the artery? That is the question, right? So what is the final question? What is the final question, ma? What is the speed of the artery? What is the speed of the artery? Okay, right. So please observe carefully what they have given. The flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. Right? That is. See here, a flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. Full stop. The wider part of the meter has a cross-sectional area equal to that of the artery. Full stop. That is what they have given. A is equal to 8 millimeter square. A is equal to 8 millimeter square. This is the area of cross-section of the wider part. Right. Now, full stop. The narrower part has an area small a is equal to 4 millimeter square. Full stop. The pressure drop in the artery is 24 pascal. Full stop. What is the speed of the blood in the artery? What is the speed of the blood in the artery? That is the question. So finally, ultimately, we have to calculate speed of the blood in artery. Okay, now see the answer. We take the density of the blood, that is generally 1.06 into 10 to the power of 3 kilogram per meter cubed. Here, the ratio of the A by A is, see, A is 8 millimeter square, and a small a is 4 millimeter square, and then if we cancel these two, what we are getting? We are getting only 2, right? Using equation, V1 is equal to square root of 2 rho GH divided by rho, that is what, rho m. This is the rho m divided by its rho into a by a whole square minus 1 whole power minus 1 by 2. This is the equation we derived in our previous class, right? That's the equation we are using now. So we take the density of the blood as 1.06 into 10 to the power of 3 kilogram per meter cubed, right? Then the ratio of the area by area is a by a is equal to, that is what, according to the given values, right? Now we are going to substitute the information what they have given. So 2 into, that is what, pressure difference they have given, no, pressure drop, that is what, rho mgh, that is 24 pascals given, divided by, and rho is 1060, right? 1060, see 1.06 into 10 power 3 means, what can we write, right? 1060 kilogram per meter cubed into 2 square minus 1, because a by a is 2, no, 2 square minus 1, it is whole power minus 1 by 2. When it comes inside the root, it will be, that is what, it comes into the denominator, and there itself this minus 1 by 2 also will be, that is what, inside the root, no, so no need to write. And because of coming into the denominator, minus also won't be there. Now if you complete this mathematical calculation, that is what, this multiplication and this multiplication, and finally this division, and the last one is square root. So the final answer we are getting 0.125 meter per second. That is the V1, that is the speed of the blood in artery, right? It is it's what happening in our human body also, but here he took example as a dog, but in our human body also, blood dose are there, right? So the blood pressure created by the heart, right? The blood has to transfer from top of the, I mean the foot, that is what, nail of the foot to the top hair. So every part of the body covers with the flow of blood, then only that part works properly, right? So blood is a very important fluid in our human body. But here, for example, he has taken anesthetized dog, whatever it may be, here they have given flow of blood in a large variety of an anesthetized dog is diverted through a venturi meter, right? The wider part of the meter has cross-sectional area equal to that of 8 millimeter square. The narrower part has an area of 4 millimeter square. The pressure drop in the artery is 24 Pascal. What is the speed of the blood in the artery? Means, that is, we have to find by using this by using this relation, that is V1 is equal to square root of 2 rho mgh divided by rho into a by a whole square minus 1 whole to the power of minus 1 by 2. By substituting all the physical quantities here, V1 is equal to square root of 2 into 24 Pascal divided by 1060 kilogram per meter cube into 2 square minus 1 will give us 0.125 meter per second. 125 meter per second. Okay, that is. Next, applications, right? Now we are going to discuss the important applications. The first is blood flow and heart attack. See, the humans dies because of heart attack. So this is the news we are listening. We listened many times, right? In our relatives and older age, and sometimes some middle age also, sometimes because of having some other health problems. So whatever it may be, what I want to say is, the important application here, blood flow and heart attack. Now we are going to discuss how the blood is going to flow in our human body, and what are the circumstances, what is the situation which leads to the heart attack of a person from this point of view. That is what, mechanical properties of fluids and pressure, right? Bernoulli's principle, equation of continuity. With the help of all these things, with the help of this concept, we can understand how the a heart attack comes to a person, right, which makes sure most of the times to leads to the death. But sometimes people's recovered, right, and there are different stages. First time it coming, second time it's coming, third time it's coming. Mostly, if it comes third time, the people will die. Okay, but in some dangerous and in some unfatal, right, in some that is what in dangerous situations, even first time also the people are going to die because of this heart attack. Okay, right, now see here blood flow and heart attack. Bernoulli's principle helps in explaining blood flow in artery. Full stop. The artery may get constricted due to the accumulation of plaque on its inner walls. In order to drive the blood through this constriction, a greater demand, a greater demand is placed on the activity of the heart. The speed of the flow of the blood in this region is raised, which lowers the pressure inside, and the artery may collapse due to the external pressure. Right? See here. I'll repeat once again. Okay? See here. The speed of the flow of blood, the speed of the flow of blood in this region is raised, which which lowers the pressure inside, and the artery may collapse due to the external pressure. Right? That is what happening exactly. The heart exerts further pressure to open this artery and forces the blood through. As the blood rushes through the opening, the internal pressure once again drops due to the same reasons, leading to a repeat collapse. This may result in heart attack. Okay, right. See, I'll tell you once again. See, here we are utilizing the concept of Bernoulli's principle to understand blood flow in artery. Right. See, it is the biological fact the artery may get constricted due to the accumulation of plaque on its inner walls. Is a biological point of view. After that, from physics point of view, the blood has to drive the fluid. The important fluid in our human body, that is blood, should be in motion. In motion, right? Okay. In order to drive the blood through this constriction, a greater demand is placed on the activity of the heart. Right. The speed of the flow, this is the important point. Please try to notice this point. From here onwards, the information is, because here he starts to give the reason. The speed of the flow of the blood in this region is raised, which lowers the pressure inside the artery, may collapse due to the external pressure. Okay, right. The heart exerts further pressure. The heart exerts further pressure to open this artery and forces the blood through. As the blood rushes through the opening, the internal pressure once again drops. That is the main problem. Due to the same reasons, leading to a repeat collapse. So, what is the reason? See, this is what accumulation of plaque on its inner walls. That is the main reason. See, when there is no chance for the flow of blood properly, the heart exerts more pressure. Right? Even though the heart exerts more pressure, at that point it overcomes. But some other point, the same problem will come, means then it will leads to the heart attack. That is what, as the blood rushes through the opening, the internal pressure once again drops due to the same reasons, leading to a repeated collapse. This may result in heart attack. Okay, right. Now, next one, See, this is what important application, blood flow and heart attack. Next, one more important application regarding the automobile and the designing of automobile. For example, here it is what aeroplane. We are going to talk about mostly aeroplane wing and aeroplane. See here. The topic name is dynamic lift. See, what is dynamic lift? First of all, dynamic lift, right? Dynamic lift is the force that acts on a body, such as airplane wing, hydrofoil, or a spinning ball, by virtue of its motion through a fluid. I'll repeat once again. Dynamic lift is the force that acts on a body, such as airplane wing, hydrofoil, or a spinning ball, by virtue of its motion through a fluid. Right? In many games, for example, see here, right? First, he told that what is dynamic lift. So, basically, what is the dynamic lift? Force, lift. You can understand dynamic. So, indicating the motion. So, force that acts on a body, such as airplane wing, hydrofoil, or spinning ball, by virtue of its motion through a fluid. Okay, that is. And now, in many games, for example, cricket, tennis, baseball, or golf, we notice that a spinning ball, right? A spinning ball deviates. A spinning ball deviates, right? A spinning ball deviates its path. That is what you can say that parabolic trajectory. Parabolic trajectory as it moves through air. As it moves through air. Okay, that is as it moves through air. Okay, ma? Right. Now we are going to discuss two important. One is ball moving without spin, ball moving with spin. Right. One is the motion of the ball in case of spin and without spin. See, spin ball has somewhat importance in cricket, right? You know that it indicates the bowling performance, right, and the bowler performance also, and it is very dangerous also. Sometimes it is easily pick up the wicket, right? So that's why what I am saying is now here we are going to talk about the spin ball, right? But in both the cases, without spin, with spin. See here, first we are going to see ball moving without spin. This is the picture. You see this picture. It is the situation where the ball is moving from here to there without spin, right? Shows the streamlines around a non-spinning ball relative, moving relative to a fluid, moving relative to a fluid. From the symmetry of streamlines, from the symmetry of streamlines, it is clear that the velocity of fluid above and below the ball at corresponding points is the same, resulting in zero pressure difference. What he is saying is, here and here, the air molecules, right? The air molecules, that is what velocity of fluid, here and here is same. When the speed of the air molecules here and here same means the pressure difference is zero, right? So that's why exerts no upward or downward force on the ball. The air therefore exerts no upward force or no downward force on the ball. That is the reason ball is moving without spin. Without spin, right? Okay. Now we are going to see ball moving with spin. Ball moving with spin. See here. Here, if you observe carefully this picture, a ball which is spinning drags air along the width, right? A ball which is spinning drags air, drags air molecules or air along with it. Full stop. If the surface is rough, more air will be dragged. If the surface is rough, more air will be dragged, right? And you can see here streamlines of air, streamlines of air for a ball which is moving and spinning at the same time. Streamlines of air for a ball which is moving and spinning at the same time. Right. The ball is moving forward and relative to it, the air is moving backwards. The ball is moving forward and relative to it, the air is moving forwards, right? That's what you can see, right? Okay, see here, ma. You can see here. That is what, see the motion of the ball and motion of the air molecules, right? The ball is moving forward and air relative to it, moving backwards. Therefore, the velocity of air above the ball, therefore, the velocity of air above the ball relative to it is larger and below it is smaller. See here, velocity of air above the ball, here it is larger, here it is smaller. So that automatically we have pressure difference. See how can we say here the pressure is larger, here the speed is larger, here the speed is smaller means, here streamlines are crowded, right? But here rarefied, below is rarefied, but here is crowded. That is the reason you can say here the speed is larger, here the speed is smaller, and the direction of the motion of the ball will be like this, and the direction of the air molecules will be opposite. Right now, this difference in the velocities of air See here velocity is larger, here velocity is smaller. This difference in the velocities of air results in the pressure difference between the lower and upper faces, and there is a net upward force on the ball. There is a net upward force on the ball. So when there is a net upward force in the ball, automatically you can say a dynamic lift which causes a dynamic lift due to the spinning, which is called as Magnus effect. So the important definition for 1 mark, what is Magnus effect, right? So what is Magnus effect means the dynamic lift due to spinning is called Magnus effect. So how what is the dynamic lift means? It is the simple thing, that is what the force that acts on your body, such as, okay, the many examples. See how the force is coming means because of the pressure difference. Why the pressure difference means because of the speed difference, right? That is what. So these are linking to one another, right? Okay. Next, one more thing. See here, that is what aerofoil or lift on aircraft wing. Aerofoil or lift on aircraft wing. Okay. See here. See this picture. It shows an aerofoil, which is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through air. Okay, this shows it is like aerofoil, aerofoil, which is a solid piece. You know, aeroplane wing is there, no, like that, which is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through air. The cross section of the wings of an aeroplane looks somewhat like the aerofoil shown in this figure, right? See this picture. Now, with the streamlines around, see these are the streamlines, with streamlines around. When the aerofoil moves against the wind, when the aerofoil moves against the wind, the orientation of the wing relative to flow direction causes the streamlines to crowd together above the wing more than those below it. So here there is a pressure difference and force automatically upward force, right? The flow speed on top is higher that the flow speed on top is higher than below it. There is an upward force resulting in a dynamic lift of the wings, and this balances the weight of the plane. This balances the weight of the plane. That is what, right? Based on this, we will discuss one example problem. But anyhow, here what he is saying is the shape of the aerofoil, that is what the shape of the aircraft wing. When it moves horizontally, it creates the pressure difference. That is what, because of the streamlines above on that and below on that, below that and above that, causes the streamlines are crowded together at top and rarefied at the bottom, means already we discussed, no, in our that is what ball moving with spin. The same situation occurs here, which causes the pressure difference. When there is a pressure difference, automatically there is a, that is what, force, right? So because of this force, automatically that's what we are calling it as dynamic lift. Dynamic lift. Okay, right. So in this class, we discussed one example problem. In that example problem, we calculated speed of the blood in the artery by having area of cross section, I mean at two different points, wider port and narrower port, by having area of cross section of wider port or narrower port. Along with that, see, by having density of the blood, right? At the same time, by also having a pressure drop in the artery. So because of these many values, substituting in the relation, that's what we derived in our previous class also, we got speed of the blood in the artery regarding the dog, not the human, regarding the dog, because the values they have given for dog, right? Regarding the dog, the value we got it as 0.125 meter per second. 0.125 meter per second. After completion of that, we came to discuss one of the important application, that is what blood flow and heart attack is a very dangerous situation, no, in humans life, right? Many peoples will die, we can see these situations in our life, right? Here the main thing is to explain blood flow and heart attack Bernoulli's principle. Bernoulli's principle helps in explaining blood flow in artery. The artery may get constricted due to the accumulation of plaque on its inner walls, right? So, because of that dropping of pressure, because of this difference in internal pressure and external pressure, and continuously the dropping of internal pressure in our artery, right? So, it leads to the situation, the dangerous situation, which is heart attack. Okay, right. After completion of that, we discussed another important application, that is what spin ball, that is dynamic lift, right? In that we can discuss a ball moving without spin, ball moving with spin. So what is the situation which leads for a ball to give spinning movement? That's what we discussed. And after that we discussed what is the situation, how an upward force exerting on aeroplane wing or aerofoil or lift on aircraft wing. That's what we discussed. Okay, right. So in our next class we'll continue with the next one more example problem. After that we'll continue with the next continuation theoretical topic. Thank you.